All right, well, I guess let's go ahead and get started. It's my pleasure today to introduce Professor Supriyo Datta from Purdue University. He's the Thomas Duncan Distinguished Professor of Electrical and Computer Engineering. The approach pioneered by his group for the description of quantum transport, which we'll learn much more about today, far from equilibrium, has been widely adopted in the fields of nanoelectronics, as described in his books, if you're familiar with them, electronic transport and mesoscopic systems, and quantum transport, atom to transistor. He's also known for his contributions to molecular and spin electronics, and has received IEEE Technical Field Awards for both research and
on slides. I actually have a full PowerPoint talk of this, and there are various versions of this here. Probably it's on the Nano Hub also. But it's just that people, my friends often tell me that it's the Blackboard talk they like much better. And part of the reason I think is that what I have to tell you is largely conceptual. And I'd say I don't years now. There's been this continuing trend is because you can pack so many of these transistors into a computer. And the way you would roughly see the numbers is that the basic device here is this transistor, which consists of a channel with two contacts across it, and this third terminal allows you to change the resistance. So it's basically a resistor which can be controlled through a third terminal. And the question is here, how much space does it take to put a transistor? Well, roughly, if it took about 10 micrometers to put one transistor, then you can see if you had a chip that was 1 centimeter by 1 centimeter, you would be able to fit about 1,000 this way and 1,000 that way. And that would mean you would have about 1 million of them, which is about where things were, say, 20 years ago. You had about 1 million. And on the other hand, if you can fit like a micron, every transistor in a micron, then you can see you roughly have 10,000 this way and 10,000 that way. And that would then give you 100 million. And today, I guess the number is about 1 billion or so. So, and over the years, then, by making the transistor smaller and smaller, essentially, people have been able to fit more and more of them. And the reason computers can do such wonderful things is because there's a lot of these switches that are acting in concert. And the more you have, of course, the more impressive it is. Okay. Now, at this time, people say that one of the biggest problems to trying to make it even smaller is the power dissipation. Because anybody who uses a laptop, you know how hot it feels. It's like it dissipates about 100 watts or so. And it's hard to put in any more transistor in there or run them any faster without increasing that. That 100 watt is kind of at a limit anyway. And so, in general, there's a lot of interest in terms of trying to find an alternative switch which wouldn't quite dissipate as much as the standard CMOS switch. And one of the candidates you often hear in this context is spin-based things. And I of course, first thing I should say is at this time there is no real clear evidence that spin will necessarily do that. On the other hand, what has happened in the last 20 years, especially the last 10 years, is that there's been enormous progress in our ability to control spins in semiconductor devices. And that's really what I'll be trying to tell you mostly about this talk. And it has come to a point where I'd say lots of the basic science is quite in place, and one can actually think about what useful things one could do with it. And some useful things are coming already, and one could specifically ask that whether you could really use this to, in a way, have a low power switch that would be actually provide some real alternative to where we are currently. Anyway, so that's kind of the thing I'll speculate towards the end of my talk. But basically, most of the talk really is about what we have learned about spin in the last 10 or 20 years. Okay. Now, before getting on to spin, though, I'd like to say a few words about this electronics from the bottom up, this bottom-up viewpoint that I think he referred to, which is what I generally talk about. And I guess there's this summer school in July for which these flyers are there. You're all welcome to pick up one. And that, in this bottom-up viewpoint, this is the thing that I have been generally always have been talking about for the last few years, is this, that when it comes to current flow in devices, our whole understanding has kind of evolved in a top-down fashion. And the reason is, of course, because 30 years ago, people had no idea what the resistance would be of something really small. Because the only resistors you could make were tens of microns long. That's where things were. I mean, when I was a graduate student, that's where things were. And a good kind of after-dinner conversation was like, well, what would happen if you really made a resistor less than a mean free path? And no one quite knew the answer. So it was kind of fun to talk about. Like the weather, you don't quite know what happened. But what has really happened, of course, in the last 30 years is it has now become much more than a philosophical question. I mean, people are routinely making devices, resistors, that are a whole lot shorter than a mean free path. I mean, in your laptop, the present day transistors, if you look at the active length here, that's like a few hundred atoms. That's where it is right now. You see, that's the commercial devices. And you go to laboratory devices, of course, it's a whole lot smaller. So today, people have a pretty good understanding. This is the thing that has happened over the last 20 or 30 years, is that people have developed a pretty good understanding of what current flow, how to think of current flow on this scale. You know, I've drawn these length scales here, and typical atomic distances are in the nanometer order. And as I say, present day commercial transistors, the channel length is around here. And people now have a very good understanding of all this, except that the whole understanding has evolved top down. And so just for historical reasons, when we think of current flow, you usually start from big things and then try to project it down to small things. And what I've been saying is that as a result, small things look a lot more complicated than they need to. And it's a much better alternative, and which I think will happen gradually anyway, is that if you take a bottom-up view, start from simple things and then try to figure out what happens when you make them bigger. Which is, you know, when you learn quantum mechanics, that's how you learn it. You start with the simplest things, like a hydrogen atom, and then you work your way up to solids. But when it comes to current flow and resistance, just for historical reasons, it's been the other way. What we understood first was the most complicated things, big resistors with lots of complicated things happening. And then you work your way down to something really simple. And just to make my point a little clearer, so for example, if you ask anybody what is the resistance of something, of a conductor, the thing that you learn somewhere up in, I guess, late high school or early freshman year is the G equals sigma A over tau. Okay. L is the length of your channel, A is the cross section. And what's this conductivity? Well, the expression that most people carry in their head is something like this: U² and tau. where n is the electron density, q is the charge on an electron, this tau is this mean free time. Because the picture people have in mind is when an electron goes through a device, it kind of goes a little bit one way, turns around, goes the other way, turns around, etc. This diffusive motion that we usually talk about. And that's mean free time is how long it goes before it scatters. Now, when you get to ballistic transport, and as I said, there's lots of, real devices today are kind of in this regime, where an electron goes from left to right without really scattering at all. And when you try to use this viewpoint to understand what happens here, you see, you get quite confused very fast. Because firstly, you don't quite know what to do with the mean free time. Now, then people say, well, what we'll use maybe is the transit time, what goes from left to right. That seems reasonable. It goes from left to right, and that's basically your mean free time, or whatever time it takes to get through. But then, with this question of what's the mass, and then also what's this number of electrons. And this is a question lately, for example, there's a lot of interest in this material called graphene. You hear a lot about it. And that confuses everybody because graphene has an EK relationship that's linear. So it looks like E equals H bar V K. So E is linearly proportional to K. Whereas mass, of course, as you know, is not the electron mass, free electron mass. It's supposed to be this effective mass, which comes from a parabolic relation like this. That's what we're used to. And then what we usually tell students is the way you should find the mass is that you should define it as 1 over m equals d2 dk2. Okay, so if you take that and make a linear relationship, you get 1 over m is equal to 0. That means mass is infinite. That's the first thing you get from that. And then you read the literature and they'll tell you, well, graphene actually is this strange material in which these are like massless Dirac particles. And so massless sounds like mass is 0. And then you don't quite know what to do with this relationship at all. And actually there's a lot of problem even with the n. Because you see the n, as you know, is the number of electrons. But then it's really not the total number of electrons. It's really supposed to be the number of free electrons. Because if you look at the total number of electrons, as you know, you take the best conductor, like copper, and take the worst conductor, like glass. They have about the same number of electrons. Okay. One conducts better than the other because supposedly some are free. And that, of course, then brings up a kind of philosophical question as to what it means to be free. And in graphene, that it can cause us problems because graphene, as you know, doesn't quite have a band gap. So you don't quite know where to start counting, etc. So you see all kinds of issues with this kind of viewpoint. On the other hand, from the bottom-up view, the viewpoint that I usually advocate would be something like this. And I'll try to justify this expression a little better in a minute. This Q squared, density of states over time. This is the conductance. And sure, most of you have probably never seen this before. Now, it's just that it's fairly easy to explain where it comes from, especially if you take a small conductor. And I'll do that in a minute. Okay. And from here, you can derive all your familiar expressions. It takes a little bit of algebra. I won't necessarily go through all that, but the point I want to make is, okay, firstly, let me explain what I mean, what these symbols are. So the Q, of course, is the same thing. This D is the density of states around the chemical potential. So what that means is the picture we have in mind is you have this channel, and the channel has a certain set of states. We have some states that are filled, some states that are empty, and usually there's a chemical potential which separates the filled ones from the empty ones. And when you apply a voltage, what happens is you have the two chemical potentials are separated in the two contacts, because the contacts are big regions with lots of states, uniform density of states everywhere, lots of them, and they're filled up to here. And when you apply a voltage, you pull this one down a little bit. Now, why does current flow? Well, because these states in here, you see electrons want to come in from here because this chemical potential is higher, so it wants to put electrons in there. This chemical potential, it wants to pull them out because the chemical potential is down here. So this contact would like to keep those states empty. This contact would like to keep them filled. What I've drawn here is, this is energy. This axis is the density of states. And for most materials, you usually have measured this, you know what these are. Usually these states are measured with photoemission experiments, so they know where these are. Now the point I'm trying to make is, the current flows because you have states that some are wanting to fill up and some are wanting to empty it. Now, do these states matter? Not really, because these states, this contact wants to fill them up, that contact also wants to fill them up, they just stay filled. Nothing else happens after that. So current flows only through those states which lie between the two chemical potentials. That's what current flows. And so finally, conduction really depends on the density of states, which is usually a function of energy, of course, but the density of states right around the chemical potential. Now, you put a bigger voltage, then you have to worry about how you average over the different energies and all, but we don't need to get into that. Point is, it depends on the density of states right there. And then this T, that's just how long it takes an electron to get from one contact to another. I mean, I'll explain this in a minute a little better. So that's it. So this, you see, kind of makes good common sense. What determines the flow? Well, the density of states, because if you wanted to know, what's the rate at which the cars go from Urbana to Chicago, you want to know how many lanes you have on your highway, and secondly, what's the speed limit on your highway? How fast it goes, and how many lanes you have. Makes perfectly good sense. And from this point of view, this is a point of view that you can easily apply to small conductors. What's more, you can easily apply to big conductors also. That's the part that is not so well recognized. That is not just a small something not only just of use here, it's really generally of use. Okay? So, for example, if you had a big conductor, then you would say, well, the density of states is proportional to the volume of the solid, how big it is. And the time, of course, how long does it take? Well, in the very small conductor, I'd say that current is interface limited. Namely, what really matters is how easily an electron gets in and gets out, which I'll write as say tau 1 and tau 2. And so this would be what I call interface limited transport. So when you're really small things, what really matters is how easily they get in and out. When you make it longer, then the important time is how long it takes to get through the thing. And so, in that case, this time is proportional to the length divided by the velocity. And now you can see that in this limit, the conductance, the L will cancel out, and the conductance will depend only on area, which is exactly what you see for ballistic conductors. Ballistic conductors, like carbon nanotube, you make it twice as long, it's still the same conductance. And you say, well, the density of states, that's proportional to volume, and the time is proportional to length and density. What about really long diffusive conductors? Well, in this limit, what is believed is that how long does it take for an electron to get from here to here? The thing is, when you have this diffusive motion, the time is not proportional to L, but to L squared. And so, in that case, this time is actually L squared divided by the diffusion coefficient. That takes some time to show, but the point is you then get Ohm's law, because you have AL here, and the time is proportional to L squared, it's like Ohm's law. So this would be the uniform view. If you start with an equation like this would be the view of how you can understand conduction at all different levels. I mean, there's lots more details one can get into, but in essence, this would be it. Okay? And roughly speaking, how do you derive this? Again, the one-line derivation is something like this, that, well, if you had just one level here, then the current would have been just one level there, Let me write it here. The current would be something like Q over T, because roughly speaking, an electron takes a time t to get from here to here. So the rate at which they are going through it would be Q over T. And when you have a distributed density of states, how many states do you have here? Well, that's like the density of states times this energy window, and that energy window is Q times V. Why? Because the two chemical potentials are separated by V. So you can multiply. So this is per state. And how many states do I have? Well, D, density of states, times Q times V. And so conductance is equal to Q squared. That would be the quick one-line derivation of what we are talking about. Okay? Now again, we can justify it better, talk in more detail, etc. But the main point I wanted to make here is that this viewpoint, what it emphasizes is what is really important about conduction. That is really the density of states at the Fermi energy, at the chemical potential. And not really how many electrons you have and things like that. And here, as you can see, you can easily apply this to graphene, any material really, because issues of effective mass don't even come in here in this context. And electron density, that's not an issue either. Now, to move on to what we want to talk about more about spin and all that, the one point I want to make here is that the argument I just made, you could say, well, it's a purely semi-classical argument. As I said, it's almost like cars on a highway. You just did counting, you get it. There's no quantum mechanics in this. But the one important quantum input into this that I want to bring in that was unknown, was not appreciated, say, before 1988. Because in 1988, there was these two groups who reported an experiment measuring the conductance of ballistic conductors, something that was really small. And what they found is that the conductance of something really small could be written as Q squared over H times an integer. That's what was experimentally shown. And that is one of the most important advances in our field. I'd say one of the most important experiments. That's about 20 years old now. And if you look at this, it kind of suggests as if this quantity, d over t, is like an integer over h. I mean, no good reason to expect that offhand. But when you know the answer, of course, there's many ways of rationalizing it. So one way you could say, well, you see what happens is, let's think of this density of states as coming from many levels, many levels like this. So if I take out an m, so you can look at the, so I'm saying q squared d over t. So let's take an m out of this, d over m. So think of it as if the density of states came from many, many lanes on that thing. And d over m is like the density of states of one of them. So you could say that one of those levels, as if it's broadened somewhat, and the density of states due to that is, and you could view that as kind of the width of this level, in the sense that, after all, the area under this has to be 1. So what you're writing here, you could view as the inverse of the width of that level. And then you could argue that, well, that's like the width of the level. So when an electron goes through, it is as if that's the uncertainty in its energy, you could argue. And then you could say, well, so that has to be greater than h. So this would be the kind of uncertainty principle argument that, as I said, I don't think it's very convincing. It's not one you would have come up with if you didn't know the answer. But knowing the answer, that's one way to rationalize it. Okay? And so the idea is that when you get to a ballistic conductor, it is as if this becomes m over h. But then, of course, this thing has to be greater than h, so conductance can always be smaller than that. But this will be the maximum you'd ever get. This is what you get in a real ballistic conductor. Now that leads to an interesting, so just to replace this, what I had here was q squared d over t, which I then replaced with m over h. That's for ballistic conductors. Now what's this M? Well, this M then is like the number of channels, if you think about it. Number of lanes on your highway, the number of channels that are conducted. And experimentally the fact is that this number of channels, what people measure when they make a channel narrower and narrower, they find that it goes as even numbers, 2, 4, 6, 7. The question is, why is it even numbers and not the 1, 2, 3? Okay. And there the understanding is that's because levels always come in pairs. To every upspin, there's always a downspin level. So they always come in pairs. And so when I draw a level here, there's always another one exactly degenerate with the same energy. And in general, when you have density of states also, I can have an upspin density of states and a downspin density of states. So I'll draw the up on this side and the down on that side. And usually, of course, you don't distinguish between the two. You just say, well, the total number is twice. So sometimes even when doing this, they put a 2 here, and then that number goes as 1, 2, 3. Because and what's that 2? And the 2 is for spin. Because usually, of course, the 2 spins don't make any difference. It's the same. It's like equal things. So it's like as if you got twice as many channels. That's all. Remember to multiply by 2. That's about it. And of course, all these spintronic devices are about trying to do something different to the 2 spins. Okay? And how do you do something different to the 2 spins? Well, the general idea is, of course, in a magnetic field, the 2 spins can separate. So you could have different channels. So you could have, the density of states for one could be different from the other in a magnetic field, for example. Now, the first experiment that's now been widely recognized and used a lot is this experiment on spin valves. And the way that works is that people have a magnet for a contact. So what that means is, like the equation I had here. Remember, write the equation here. So the way you think about this is that in the magnet, the 2 density of states are now different for the 2 spins. So if I draw the magnet density of states in the magnet, it will look something like this. So again, I'm drawing the upspin and the downspin. And in a magnet, one is shifted with respect to the other. In all normal materials, they would have been right on top of each other. But in a magnet, they're shifted. And the same on that side. Magnet, shifted. So what that means is that when I look at this time is defined as, if I put an electron here, how easily it gets out into the contacts. Right? And as I said earlier, that in the interface limited transport, you would have said, okay, this time, total time is like tau 1 plus tau 2. Tau 1 is the time that it takes in terms of getting out into a contact on this side, and tau 2 is the time for that side. Yeah, you add the two, that's it. Now, when you have a magnet for the contact, the thing is that one spin gets out much more easily than the other. And so, what you might expect then is that here, for one type of spin, let's say the time is tau going out, and for the other type of spin, it's very hard to get out. So let's say I put a capital T. It takes a very long time to get out for the other type. Because you have so few states there. And of course, ideally what people would like to do is make this density of states so small at the chemical potential that this spin can't even get out. That would be the best spintronic contact. That's what they really want to try to do. And if you could do that, then the capital T would have been infinite. In the real world, I guess it's not infinite really, but they get a good ratio between the two. They get 4:1, 5:1 ratios these days. Okay. So what that means is that for one type of spin, it will be, the total time would be 2 tau. So, and for another type of spin, the total time would be like 2t. And so the conductance will be u squared d over 2. D over 2 because d is like the total density of states, we are just using half of it. And then one of them takes a time tau, the other takes the time t. So this would then be the resistance you'd expect. Now the interesting thing is, what makes this effect very useful is that the resistance is higher if the magnets are pointing in opposite directions. That is, if instead of parallel, that's called the parallel configuration, if you actually had an anti-parallel configuration. So if this was anti-parallel. Why? Because now what would happen is, one type of spin would get out easily on one side, but it would be very hard to get out on the other. And the other type of spin would get out, would have a hard time this way, but would have an easy time this way. So what that means is the total conductance would be the same for both types of spins, because either one is like tau plus t. But then there's 2 of them, so it will be, instead of this, you'd have like 2 over tau plus t. And you see, with a little algebra, you can show that this is always less than that. Now, the limit that's very easy to see is, what if tau were infinite? If you really had perfect contacts, then you can see it easily. Because then it means in the anti-parallel configuration, no current at all. That's infinite. Because what happens is one spin gets in but can't get out, and the other spin can get out but then can't get in. So neither can conduct. Whereas in the parallel configuration, of course, this is dropped, but then there's one spin that goes right through nicely. So you have good conductance. And what you can show is that regardless of the ratio between the two, the parallel, this is what you call the parallel, and this is what you call the anti-parallel. The parallel conductance will always be greater than the anti-parallel conductance. Which means the resistance, of course, will be the reverse. And this is something that has found widespread use. People say this is one of the things that went from laboratory to application really quick, like between 1988 and 1998, because it was used for reading magnetic information. That is, magnets usually store information in the form of the magnetization of this magnet, and so depending on whether it's up or down, the resistance changes. And in those early experiments, I think it changed a little bit, more like 5% or less. But it was called a giant magnetoresistance because that was in those days really big compared to anything anyone had seen. And it found use very quickly in terms of reading the information. Just from that change in resistance, you could tell whether the magnet information was this way or that. Now, so that's the spin valve device that you hear a lot about. And one thing that kind of followed from that in the next 10 years is something called spin torque. And the spin torque device, the way it worked was something like you see, with the spin valve device, you can read the information, but you still cannot write it, because if you want to actually switch the magnet, the way you do it is you put a real coil around it and create a magnetic field. That's the only way to turn a magnet, 10 years ago at least. But what people found was that if you, let's say, it looks like this, so it's anti-parallel, and you run a current, if this magnet is thin enough, thin meaning like 2 nanometers or so, not a big thick magnet, but just say 2 nanometers. So it's like a thin magnet and the real contact comes after. So this is just a non-magnetic thing, but you have a little thin monolayer there. Then what they found is when they run a current, with enough current you can actually turn it. You can turn it. That's the spin torque effect. And that's why this again I consider is a major advance here. Because as I say, 10 years ago if you ask someone, how do you turn a magnet? Well, you turn it the 19th century. You put a magnetic field. That's the only way to do it, run coils around. But now I'd say there is now clear experimental evidence that you can actually turn it by just running spin currents. In other words, where what you're doing is you're injecting spins from here. This injects a particular electrons with one preferential spin, and enough of them get in here that they actually turn that. That's now demonstrated. And what that means is, again, now lots of interest in this because what that means is you not only can read information, you actually can write information also. Now, just to understand where the magnitude of this effect, I'd like to stress is, you see, I mentioned that in a magnet, what happens is that up and down spins have their energy, this density of states, split by a fairly large amount. Now, why do these states split? Well, the general understanding is that every electron is kind of like a magnet. Ordinarily, most materials are non-magnetic because there's as many, because they're all random. Whereas in a magnet, they all happen to get lined up. Now, how do you know that every electron is a magnet? Well, that goes back to this old Stern-Gerlach experiment. That is, that in an inhomogeneous magnetic field, what is well known is that little magnetic dipoles want to deflect. And if you had a magnetic dipole in one direction, it would deflect in one direction. If it were in the other direction, it would deflect the opposite direction. That's a well-known macroscopic effect. That's widely used to separate magnetic particles in the laboratory. But when this experiment was done with electrons, actually it was done with hydrogen atoms. Originally with silver atoms and then with hydrogen atoms. They found that, that some electrons deflected upwards, some electrons deflected downwards. And from that, they could deduce what the strength of the magnetic moment of each electron is. And that's the Bohr magneton. The Bohr magneton, that's this QH bar over 2m. And that comes to about 10 to the power minus 23 amp square meter. That's the strength of each one of these. Okay. And when you put them in a magnetic field P, what happens is, then the energy of one of them goes up by mu b times b and the other goes down by mu b times b. Now what you can check easily is that mu b times b, if I had 1 Tesla, so 1 Tesla means this is all in MKS units, then the energy would be 10 to the power minus 23 joules, which is actually sounds like really a very small energy, because as you know, the way you usually think of whether an energy is important or not is how does it compare to kT. And kT, as you know, is room temperature 25 millivolts. If this I convert to electron volts, it would be 0.06 millielectron volts. Sounds like a very small number, which is why normally you don't worry about it too much, unless you are at really low temperatures. But the fact is that in these magnets, that splitting is like 1 electron volt, which corresponds to an enormous magnetic field, if you think about it. Like something that you normally never have. Like when you go to a high magnetic field facility, you usually have something like, say, maybe 10 Tesla, 100 Tesla, and you have to leave your credit cards outside. And this, you can see, we are now talking of 0.06 millivolts. To get 1 electron volt, you're really talking of the equivalent of something like 10,000 Tesla. 10 to the power 4 Tesla. And that's what people refer to as this exchange field. You see, which there's no good simple explanation for it. But the experimental fact is that even if you take iron atoms, as you know, iron has an atomic number of 26, which has 18 core electrons, and then there's the d electrons, 6 of them, and then there's the s electrons, 2 of them. And you would have expected these valence electrons to be just half up and half down. But what was known from the days of atomic physics in the first experiments, that in practice, they actually want to line up. These 6 electrons, because of this what's called Hund's rule, 5 line up in one direction and 1 the other way. So there is this enormous force that wants to line them up. And that's what is generally what's referred to as the exchange field. And this is something that even in a solid iron, it is like all the electrons want to line up. And I think per atom, they have about 2.2 spins per unit cell. That's measured in iron. And this is the thing for which there's no simple explanation. It goes beyond classical theory. It has to do with this exchange and this Coulomb repulsion and the exclusion principle, which leads to this enormous exchange field. Okay? But that's all established. Now the point I want to make, the reason I think is interesting here is this, that it gives you, in order to understand the nature of this spin torque, the point I wanted to make is, that you see, spin torque, usually when you do not have an effect if both magnets are exactly lined up. As long as there's a little bit of an angle, that's when you see the effect. So in order to turn that, there has to be a little bit of an angle, which even if they are kind of lined up, because of thermal fluctuations, you always have that. Now, and the way you understand it is that when you put a bias on this, these spins get injected here and they create a non-equilibrium spin density in this magnet. So what I mean by that is this magnet left to itself, all the spins would be parallel to this. But when you apply a voltage, you're actually injecting some things that come in at a bit of an angle. Now you might say, well, that's just a small perturbation. So I mean, after all, there's 2.2 spins, as I said, per unit cell in that magnet anyway. So what happens if you just put in a part per million? How does it matter? Well, the thing is that the magnet does not feel any force due to any exchange field that is in this direction. Because what is known is that magnets, when given a field, they want to rotate around it. If they're in the same direction, it doesn't feel much. So this magnet, as long as all the fields are in this direction, it's not responding at all. But just a little bit in this direction, that will get it moving. And how big is this? Well, the point is, if you had like 1 spin per unit cell, it would have given you 10,000 Tesla. Let's say you have only 10 to the minus 6 spins per unit cell. That would still give you 100th of a Tesla, which is like 100 Gauss. Now 100 Gauss, of course, is small compared to that, but you see, that's kind of the fields you really need to turn a magnet. That's the point I'm trying to make. That just 1/1,000,000th of a spin per cell, unit cell, is good enough to give you an effective field of 100 Gauss to turn. And what makes the spin torque so interesting and so effective from a practical point of view is that, firstly, you are getting these enormous fields, effective fields with relatively low spins. And secondly, of course, it's focused. Focused in the sense that exchange forces only act between magnet electrons whose wave functions overlap, not if the wave functions don't overlap. If they don't overlap, then the standard classical understanding is fine. There's no extra forces. So what that means is you can turn a magnet right here and not affect a magnet that is 1 nanometer away, because the wave function doesn't overlap. Whereas, if you are trying to turn it the old-fashioned way with a magnetic field, anything you do here will affect something next to it. So these spin valve and spin torque, I say, is two things that happened in the last 20 years, one after the other, which I think kind of really make these two different fields, the field of spins in semiconductors and the field of magnets, kind of, which were two totally distinct fields. That magnetism was something totally different from spintronics, but now it's really become kind of one big field. And there's one other thing I want to add to this, and that's also been observed in the last 10, 20 years, is that these effects due to spins don't have to be local. Local meaning don't have to be in the path of the current. That is, what people have seen is the following. Supposing you're running current in this direction. So what happens is when you inject this, let's say, is a magnet, which injects a lot of spins of this in this direction, and very few spins in the opposite direction. So in here, if I were drawing the number of spins, I'd see lots of them here and not so many here. And they would, of course, want to spread out like this. Over a distance, that's like the spin coherence line. Because they wouldn't just stay here, they would diffuse way out here. And they would gradually recombine. So it's almost like in a bipolar transistor. So a little bit like minority carrier spreading out, if you're familiar with that. But anyway, but the point is that if you looked at spins of one type, they're spreading out this way. Spins of the other type, they're going this way. And if I put another contact here, which is non-magnetic, it would measure the average chemical potential. Like you could think of these as the quasi-Fermi levels for one type of spin and another type of spin. And this one would measure the average value. On the other hand, if you put another magnet here, it would measure that value. And if you had put a magnet in another direction, let's say pointing this way, then you would have measured that value. So what people have seen, again experimentally observed is, you can run a current here, stand at a point 1 micron away, like a spin coherence line, which varies from one material to another. And with a magnet, you can measure a voltage. So if you put a magnet this way, you measure a certain voltage. If you put a magnet another way, you measure a different voltage. And this is higher than that. So you can see the effect of spins at a distance, far away. And the other interesting thing here is that this and this, I say if it is parallel, you see one. If it's anti-parallel, you see another. Now what if it is in the middle? Let's say it's like this. Well, then it is somewhere in between. Actually. So what can be mapped out is that the voltage you measure out there as a function of the angle will look something like this. So this is the case when they are parallel, this is when they are anti-parallel, and then somewhere in between. So it's a continuous thing. See? And the one interesting point I want to make here is that that curve actually can be written as cosine squared half theta. In the sense that when theta is 0, it's a maximum. When theta is 180 degrees, that's like anti-parallel, that's when it's a minimum, because it's now cosine square of 90 degrees. And then when it goes back to 360, it's again a maximum, so it oscillates like that. And this is where it's a little bit, when in our understanding spin, I often say that the nearest analogy, if you have not heard of it before, is the polarization of light. That with light, as you know, you could have a polarizer like this, and an analyzer that's at 90 degrees, and it would block it. On the other hand, if they're in the same direction, it would let it pass. So this is a little bit like that, you see. But there's a very important difference though. And that is, with light, it would have been cosine squared theta. Whereas with electrons, it's cosine squared half theta. And fundamentally, of course, that's related to this half integer spin, etc. But the experimental consequence of that you see right away. That is, with a polarizer and an analyzer, the way to block is, if your polarizer is this way, you put the analyzer at 90 degrees. That's how you block light. With electron spin, if your injecting magnet is this way, the way you block it is by putting a magnet anti-parallel, not at 90 degrees. 90 degrees wouldn't be a minimum. Minimum would be at 180 degrees. And that's just this theta and half theta. 180 degrees is kind of like 90 degrees. And that leads to this whole different thing that one has to get used to when dealing with spin. That is a lot like polarization, except that light polarization we think of in terms of vectors, whereas here you think of it in terms of what's called spinors. And because this difference, that's the part that you have to get used to somehow. But these are all experiments that, as I say, are now being done on semiconductor devices. That's the part. Some of this physics, of course, has been known since the 1930s and all, when people first started, after the Stern-Gerlach experiment, when first people learned about spin. And you'll see on the web, you see lots of, I guess, demonstrations that people have developed for physics classes where they try to talk about Gedanken experiments with which to understand this, how spins rotate and so on, the properties of spin. And the point I wanted to make is that you don't really need Gedanken experiments anymore. It's like these are all experiments people are doing in the lab with real semiconductor devices. And the understanding has come to a point that you can actually think of not only understanding the basics of spin, but in terms of you can start thinking of how to use all this. So for example, I said here about how if you turn the magnet, the spin would oscillate. But actually, the way the experiment is often done is you don't turn the magnet, you keep the magnet fixed. But what you do is you apply a magnetic field in this direction. Because what a magnetic field is supposed to do is, if you inject a spin this way, it will rotate around that magnetic field. So what can happen is, so this angle can be changed by changing the magnetic field. So as you get from here to there, it might rotate by that amount. Or depending on the magnetic field, it might actually rotate backwards. And then, of course, the signal will change. That's called the Handler signal, again, that people have observed in a lot of these devices now. And the picture that I think I've used in the abstract, that's from a recent science paper where they do not use a magnetic field. What they use is a material with spin-orbit coupling, where actually when you put an electric field in this direction, that gives rise, because of the spin-orbit effect, gives you an effective magnetic field, which causes the thing to turn. So all these very subtle experiments that people are doing. But the one point I also want to stress again is that in addition to the spin injection and manipulation, there is this spin torque, which is what people have also shown is the following, that you can run a current here, and if you run enough current, that magnet can be made to switch by spin torque effect. And to me, that sounds amazing. You see, you're running a current here. Here's a magnet sitting by itself, minding its own business, completely out of the current path, and at some point it gets flipped. Why? Because of all these excess spins that pile up. And again, depending on whether you put a magnetic field or not, you can make it flip back again. So, and some of those experiments people have done, and some they are doing right now. Lots of these interesting things. So let me just finish up then in the next 5 minutes with saying that the question that often people ask then is, well, so from an applied point of view, where can one go with all this? And the one thing I like to mention here is the following. You see, the way you usually CMOS works, CMOS logic, or the kind of switching we are used to works, is you have a device, and by putting a voltage, you can change its resistance. As I said earlier, the important central device in CMOS is this, the field effect transistor. What it does is by putting a voltage here, you change the resistance, typically by 4 or 5 orders of magnitude. Like today's devices, you say it goes from 10 kilo ohms in the on state to that 100 mega ohms in the off state. And so the idea is that if this capacitor is charged, like 1, then these devices are arranged so this is in its low resistance state, that's in a high resistance state, and so this voltage is close to ground, and so you get a 0 there. And if you put a 0 here, then you get a 1 there, because the resistance is switched. That's how the usual CMOS logic would work. And when people talk about, well, how do I use spin? The thinking usually is that somehow using spin, you have to figure out how to change the resistances. And so from that point of view, the way you think is, well, you see, I can change that voltage out there by changing the field here, for example. But when you think that way, you don't see any real advantage relative to CMOS. Because the voltages that one measures experimentally are typically tens of microvolts. And then how do you, again, turn it into a gate voltage that you can actually use to drive the next stage? That's not at all clear. Because finally you have to make circuits out of it. This has to drive the next thing, and then the next thing. And so, as long as you're always thinking in terms of how to work with charge in the big scheme of things, and the spin is just an internal thing, I don't really see how one could go very far with it. On the other hand, what one could do is the following. you could say that we won't really try to convert to charge at all at every stage. So you see, the way this is working is, information is stored in the form of charge, and you use this to transfer information from here to here. Only information is transferred. Energy comes from there. Energy comes from the supply, not from your information source. But what one could do is, with that same attitude, you could say, the information is the magnet. And so and this is the power supply. So when I run a current here, what happens is, depending on this magnet, that magnet can switch. I don't need to take the voltage out and try to drive another stage. The point is, this is done. And then I could have a barrier here, and then there could be a next stage here. So this then can drive the next one. So in principle, you could have a shift register where the information is not in the form of charges on a capacitor, but rather in the form of just magnets. The information can be in this form of magnets. And then you convert to charge only at the end of the day. Only after you have done what you want to do all kinds of operations, do it at the end of the day. Instead of doing it at every stage. So and all this, of course, 10, 20 years ago wouldn't make any sense, because you wouldn't know how to convert the spin back into a magnetic information. Those were two totally different things. But now that all this has become one big field, you can think of things like this. That you see, there's a magnet which has information. When you put a voltage on it, you inject spins in here. What you inject here is like analog information. And then this next magnet digitizes it. Digitizes in the sense that if the analog signal exceeds something, the magnet flips. If it doesn't exceed, it doesn't flip. So this is why I feel that I think this field has now come to a point where it makes sense to think from an applied point of view. You see, for a long time, for the last 20 years, I've often been asked to talk about spin. And in the 90s, I usually would say, well, there isn't really very much that has happened in the field of semiconductors. It's really not worth talking about, because most of the important action was in the context of metals. There's some interesting things there, but nothing in the context of semiconductors. Since 2000, there's been a lot of interesting experiments on semiconductors. And so in the last 10 years, sometimes when I talk about this, I say, well, yeah, there's lots of very interesting science here, but nothing from an applied point of view. You should just view it as science. But now I feel it has come to a point where I think the knowledge base is there, the science is there, and it is important to think from an applied point of view. And which is why I now feel that, well, if you are getting a degree in electrical engineering, you should know a little bit about how to think about spin and this whole class of devices, because I think you'll hear more and more about it. Thank you.
So at this point, the talk's open for a few questions. Any questions for Professor Dodd? Or we could just go out and you can go out there in the hallway.
So what's the implication of this on scaling or power dissipation?
Yeah, very good point. Because as I say, CMOS is so good that I'd say the only reason to think of any alternative would be if it was low power. Okay? And that is where, based on estimates, people say that there is a promise for going to low power, but I'd say it's not demonstrated really. And the reason would be something like this, that if you look at either the dissipation, the energy needed to switch. In the case of CMOS, you'd estimate that for first switch as maybe a femtojoule or so. Whereas, in this context, I think what has been demonstrated, the smallest ones would still be bigger than a femtojoule. Let's say somewhere between 1 and 10 femtojoules. Now, could it be smaller? The understanding is that both this and the switching time are proportional to the number of spins involved in the magnet. And whatever number of spins there are. And all the experiments tend to be with today's magnets, which have, let's say, a few million spins. Whereas, to be a magnet, it needs to be about 1,000 spins. So there are magnets which are only 1,000 spins. So in principle, what it seems, one could go to much smaller magnets and thereby reduce both the dissipation and the switching time in office. Because time especially is one that strikes you, because you process of switching a magnet you think of as a relatively slow process. Maybe even nanosecond sounds too short. But experimentally people have now shown that these million spin magnets can be switched with, I think the fastest I know is like 100 picoseconds. And probably could be made shorter. So I'd say that with small magnets, it is possible that numbers will look attractive. And the more important part I feel is probably with all the other interesting things you could do, because when you work with charge, it's just 0 and 1. Whereas this being spin, it is kind of a vector. And that allows you some latitude, that allows you things on the lines of neural networks and other things which one could probably come up with. So that's about what it is. But as I say, most of the talk is about science. This last part is science fiction. We don't know.
When you do this magnetic talk, you're passing a current. Where does the coherence time come into that? Magnetic coherence time. I mean, you want a difference between the two polars, the difference between the two magnetic spins, right? And the system and equilibrium should be half one, half the other.
But by applying a voltage on this, you are creating a non-equilibrium situation, because you have two different chemical potentials on the two sides, and you have the voltage between them, and so in between, this region is really out of equilibrium, because it's not quite. This side is one type of equilibrium, this side is a different type of equilibrium, and what's in between is out of equilibrium. That would be true of any device. With spintronic contacts, they are also out of equilibrium in a spin sense. So you'd say as if the two spins have two different chemical potentials, have two different quasi-Fermi levels. So it's out of equilibrium. Whereas ordinary devices, usually both spins are in equilibrium.
So a coherence time has no.
Coherence time would determine how much out of equilibrium you can get. So if it's a material with a long coherence time, like in silicon, people say that the coherence lengths I've seen tens of microns actually. So whereas copper, it would be more like 1,000 angstroms. So yeah, so those are important. And to some extent, I say when you look at semiconductor devices, people say that you can drive the conduction band and valence band out of equilibrium, because the rate at which decombination generation processes happen is like a nanosecond. So you can drive them somewhat out of equilibrium. So here it's like not conduction and valence band, it's like upspin band and downspin band. But because the communication is relatively weak, you can drive them out of equilibrium.
Okay, well, I don't mean to cut the questions short, but in the interest of time, I think we're going to go ahead and talk. If you have questions further from Professor Dada, we can go ahead and ask them out in the lobby while we